Doppler shift. Basically, what it is that the frequency, how it sounds to you, depends upon this frequency, basically. I mean, if somebody speaks at a, like I mentioned, a very common fact is that the female voice has a higher frequency than the male voice, right? And so when you hear, your ears figure out what frequency it is, and it figures out whether it is a male or a female, right? Now the interesting fact is, so you just measure, your brain measures the cycles per second and figures the frequency, figures out the frequency. Now the interesting thing is, if you are driving in a car, moving, then what will happen is, when you are moving towards the source of the sound, you are going to get more cycles per second than that being transmitted. Does that sound like common? I mean, this is what is being transmitted, but if you are coming, you will get more cycles per second because you are just moving towards the source. On the other hand, if you are moving away from the source, you will get less cycles per second. Right? So the same sound will sound different, and then you will know whether the train is coming towards you or the train going away from you. How do you know? Because the frequency changes. That is a Doppler shift. If you hear a sound and it looks like the frequency is going up and up and up, then you know that something is coming towards you. On the other hand, you are standing right there, but the frequency is going down and down and down, then you know something is going away from you. So that's how you know whether the train is coming or going, or bus is coming or going, or you are coming or going, you know, whatever it is that is moving. Right? And so Doppler shift is very easy because basically the frequency difference, the change in frequency is simply your velocity divided by the wavelength. If you are going, suppose the wavelength is 5 meters, and if you are going 5 meters per second, you are going to get, 5 meters more, 1 cycle per second more. Right? Common sense. So what you do is you find your velocity in meters per second and find the wavelength in meters, and divide that, and you get basically the difference. Alright, so here is an example. This says nu f divided by c. So let's say take the example first of all. So let's say we use 2.4 gigahertz. Okay, and that is equal to 12.5 centimeters. We had calculated that before, by the way. I mean, I forgot to do one thing. I should have given you homework, so that given a frequency, you should be able to calculate the wavelength. Right? This is the homework for today anyway. It's coming up in a minute. But basically, I should have given you last week. So, given that it is 2.4 gigahertz, that is the frequency your Wi-Fi uses, by the way. That is the frequency that your Bluetooth uses. That is the frequency we all use in everything that we use at home, including your phone, by cardless phone. So, 2.4 gigahertz is a very common frequency. It has a wavelength of 12.5 centimeter, which I have written here as 0.125 meter. Okay, so you can calculate the wavelength. Now, if you are going at 120 kilometers per hour, you can calculate that, translate that to 33.3 meters per second. Right? So the frequency difference is simply velocity, which is 33.3. divided by the wavelength 0.125 is 267 hertz. So the frequency will be 267 hertz different than what it is being sent at, depending upon whether you are going towards it or away from it. Is that clear? How the Doppler shift is created? You have to calculate the wavelength, and wavelength tells you how many cycles you can get in that with that speed more than if you are not going at all. Not moving. And it doesn't matter who moves, the source or yourself. If the source is moving, you are stationary, you are going to get more or less cycles. Yeah.
So if you're on your cell phone in the car and you're transmitting and receiving data, like how does it know how fast you're
going? Exactly. So basically what it is they can figure it out that you're going at 120 miles per hour and give you a ticket right there. Yeah, so that actually will come up. When we talk about mobiles, basically the thing is we have to be, if you are going to do anything with the frequency and your frequency is going to change, then I have to be allowed for the possibility of you moving at 120 kilometers per hour, because that's a normal speed. 120 kilometers I think is 60 miles per hour. Something like that. Anyway, so the idea is that is the speed which people are going to go in the car, and so their frequency could be off by, so much, and so I have to be able to forgive that. Now, what if there's a reflector? So you are driving around a mountain, having nice scenery, and you are also getting a cellular signal. You're going to get two signals. You're going to get direct signal, and if you're driving in this direction, then you will get less frequency than what is being transmitted, but you will also get a reflected signal, and its frequency will be increasing because you are going towards it, right? So two rays will be received, and the difference between those two would be 2f v upon c, 2 times the Doppler shift. V is the velocity. I was saying nu before, so that was wrong. If v is the velocity, which is what is speed you are going, c is the speed of light, and f is the frequency. So anyway, so it will be 2 times the Doppler shift, and so they will add or cancel out each other as the receiver moves. So coherence time is the time at which the channel response is constant, and so that is called 1 upon the Doppler spread. So what happens is, basically what if you measure this for some time, the two waves will add, and for other times they will be out of phase. So, and sometimes they will be in phase, and sometimes they will be out of phase, right? So they will add, and sometimes they will subtract. All right, but there is some slight period over which, let's say they add and then they subtract. So that time is called coherence time, right? And that will be just opposite of the difference. So whatever is the Doppler spread, which is 2 times the Doppler shift, okay? Doppler shift we calculated before. Twice that is called Doppler spread, because, plus and minus. And 1 upon that spread is called the coherence time, during which, it will always be adding, and then it will subtracting for another coherence time, and then adding, right? So the channel response is one way. During that time is called coherence time. So we will use that term, coherence time, Doppler spread, Doppler shift, and the relationship is clear now, right? Doppler shift is Fv upon C. Spread is 2 times Fv upon C, and the coherence time is 1 upon 2 Fv upon C, whatever. Any question about the Doppler? Yeah.
So there is no difference that which of these signals they filter out?
Which among these two signals?
Yeah.
Oh yeah, actually, so they will have a different magnitude for sure.
Yeah,
if this is one transmitter, and then we will talk about that multipath in a minute. So that is a different lecture coming up. Now duplexing, it's a totally different concept. Duplexing is basically the directions which the traffic goes. Now what we could do is we could have two frequencies. On one frequency subscriber talks to the base station, blue frequency. On the other frequency, the base station talks to the subscriber. Now both of them can talk at the same time. Both of them can talk at the same time, and that would be basically frequency division duplex, FDD. FDD, this is we call FDD because first of all we are frequency division full duplex actually here. Full duplex means, okay, so everybody understands full duplex and half duplex, right? Somebody doesn't know half duplex? Let me explain. So if you go on the road here outside, big road, what is the name of the road? Forest Park Parkway. So the traffic can go in both directions. So that is called full duplex. But if suppose one side is closed because there is an accident or they are making construction, then what happens? Then they close one side and then they put by a guy with a flag, says stop, you cannot go. And then one side goes and then they put a flag on the other side and the second side goes, right? So that is called half duplex, because still the traffic is two-way, but it is alternating. Half duplex. Or full duplex means you can go at the same time. So this is full duplex. On the top is full duplex. However, we could also do so that we could do half duplex, so that we could do for some time base station talks and then the subscriber talks and the base station talks and subscriber talks. So this half duplex is called TDD. TDD means time division duplexing. The two sides divide the time. In FDD, two sides divide the frequency. Right? We call it full duplex. FDD and TDD is now. Now in the TDD, in FDD, basically the frequencies don't have to be equal. I mean, you could give 100 megahertz to the base and 10 kilohertz to the subscriber. Similarly, the time division duplexing, the time does not have to be equal. You could give as much time to the base as you want and less time to the subscriber and vice versa. Right? So that is TDD FDD. So the most new technologies use TDD. And we talked about, remember TDD LTE, time division LTE other day. That is because now the traffic is very asymmetric. Because we listen to video, we watch more video than we transmit our video, and therefore there is more going in one direction, and so that can be easily done with TDD. If you want to watch video, we start giving more time to the base station. If you want to talk, then we start giving more time to you, or something like that, right? With FDD, you cannot change that. Frequencies, once it is allocated, it is allocated. I mean, like frequencies, generally they keep equal, by the way. So in FDD, what they do is they give you 30 kilohertz on this side, 30 kilohertz on this side, and then you just cannot make it 300 on one side. Okay? So FDD is kind of static. TDD is dynamic. The word dynamic means time changing, which is, it is, right? So TDD is what we need for tomorrow's network. For yesterday's network, where we were all talking on the phone it is 50-50. I talk 50, you talk 50. If you talk 100, then we're not very good friends. But so basically it is 50-50, 50 coming down, 50 going up, right? In video, it is not the case. Yeah.
If you had a peer-to-peer system for a video, you'd probably prefer the FDD, right?
Yeah. So the thing is, FDD, yes, you prefer means basically if you have a peer-to-peer system, yes, it would be good, because then that's why they are trying to make it remember we talked about this, that P2P video is coming in because the network that were designed for symmetric traffic, they cannot take this asymmetric traffic. So they can make it more symmetric by putting P2P. Although in P2P everybody lies. Now remember, those of you who do P2P, you don't send out at 2 gigabits per second, you send out at 40 kilobits per second and you receive at 2 gigabits per second, right? So it is still asymmetric. And the reason it is still asymmetric is because that is how the networks are designed. If you think about not the telephone networks, but if you think about DSL is asymmetric, right? So a lot more can come to you than can get out from you. Upload speed is very low. So when you get a DSL connection from AT&T, you only can send 500 kilohertz, while you can get 5 megabits. You can send 5 kilobits. So 1:10 ratio. So that's why you don't want to upload at symmetric rate. So here I think you can design a network for symmetric traffic. You can design a network for asymmetric traffic, and then you have to match the traffic to the network that is designed for. Right. So that's the point. Okay. All right. The point here is that it says most WiMAX. I should change it. Most LTE deployments will use TDD because you can quickly change up and down rate. Having said that, it turns out in practice you cannot change it, and I will come to that when we talk about TDD, LTE, or whatever. So then we'll see as to why it cannot just change it. Yeah.
I'd like to ask you. I think then frequent FDD is better for gaming videos than the TDD.
is better for?
Gaming videos.
Gaming.
Yeah.
Because gaming is more symmetric.
Yeah, I think so.
Yeah. I mean, basically FDD is past, TD is future. The past was voice. Right? So that is why all the previous networks were designed for FDD. Period. That's it. So your old telephone network at home, your old telephone network on the cellular, everything was designed for FDD. Right? All the traffic was voice. But with the internet coming in, the ratios are changing. So then we are thinking about TDD. Alright. So TDD is designed to prepare the spectrum. With FDD, you need twice the frequency. Here with 30 kilohertz, you can both talk, right? And easy channel estimation. And there is another advantage of this is that now when you receive this, you know that how much noise there is, and then you can change your transmission to match the noise. Here, you don't know how much noise it is because you never receive your own signal. When you don't receive the signal. Basically, what is happening is I am transmitting at this frequency, so this guy is getting the noise, but we don't know how much that noise is. Well, I am receiving at this frequency, so by receiving signal, I cannot figure out what is the noise. Here I know because we are both transmitting on the same frequency. Right? So we both see the same noise. Right? So this is better in that sense. Easy channel estimation. Channel estimation means figuring out what the channel is. Negative is all neighboring BSS should time synchronize. So then the problem is that if there are two base stations and one says I want to transmit and this one says I want to transmit, there is some complex interference between them, and so you cannot be, so there is a problem there which we will talk about when we come to that point. Okay. So that brings us to the end of this on the last minute. Basically 5 key points. Electric, radio, light, X-rays are all electromagnetic waves now. You know that, right? And wireless radio waves travel at the same speed of light, and the wavelength can be calculated by lambda is equal to C upon S. Third thing we learned was QAM. So we now know 16 QAM uses 16 combinations. That means 4 bits per symbol. And hertz and bits are related by Nyquist and Shannon's theorem. The Nyquist just doesn't vary about the noise, it just varies about the levels of your signal. And the Shannon's varies about the noise, and those are the limits. And frequency hopping and direct sequence we talked about, those are the CDMA methods. Right? Now, there is a homework, and this is due next Monday. Alright? And so you need to practice all about how to calculate the wavelength, how to calculate the power, and here's the dBm. This is how we measure the power, 30 dBm, 20 dB, and so on and so forth, right? And that's the end.